Welcome back to multivariate calculus. In this video, we're going to be looking at spherical coordinates. If you're anything like me, the discussion that we had previously on cylindrical coordinates is a little bit disappointing. It feels like the cylindrical coordinates don't give us that nice benefit that polar coordinates gave us in 2 dimensions. Specifically, if I get my head out of the way so that I can draw in some coordinate axes here, let's set up x, y, and z in the usual sense. Let's find our point here called x, y, z, and draw in all of the usual lines showing us how we can get this point from the usual setup. Now, the thing that I generally introduce polar coordinates to in my trigonometry and pre-calculus classes is it has the nice advantage of having one measurement that goes from the origin directly to the point in question. And so I want to have a coordinate system that has exactly that. Let's go ahead and call this measurement rho, Greek letter rho, which kind of looks like a curly P. I see a lot of sources that use R for this measurement. I'm using rho specifically because we've already used R to mean the thing in cylindrical coordinates. And I'm going to be doing a lot of converting between cylindrical and spherical coordinates, so it's going to be a little bit challenging. Now, we already have one angle that we've been discussing here, which gives us which direction we're looking in the XY plane. That's a really nice angle. We can stick with that. But it doesn't quite give us everything we need in order to understand the direction that this rho is pointing at. Unfortunately, at this point, there are 2 schools of thought. Traditionally in mathematics, we're going to measure another angle coming downward from the z-axis to wherever that thing is sitting. We're going to call that angle phi. Once again, to make things confusing, depending on what source you look for, sometimes you will see phi and theta swapped. So you have to be very careful. We're using theta to mean the angle in the xy plane because that's the value that we learned in polar coordinates, and we used that in cylindrical coordinates, and we're going to want to do some converting between the two. But sometimes you see these in the other direction, so you have to be very careful and pay attention to the meaning of the symbols whenever you're working in spherical coordinates. To make things even more confusing, the most popular and the most common application of spherical coordinates, the one that I guarantee that you have seen before, doesn't use this definition. Instead, we measure up from the xy plane. So that we can go from positive 90 degrees pi over 2 to negative 90 degrees pi over 2. And in fact, this definition, instead of letting theta go from 0 to 2 pi, 360 degrees, we're going to go from negative pi, negative 180 degrees, to positive pi, positive 180 degrees. The application that I'm talking about is latitude and longitude on a globe. The way that latitude and longitude are defined, I want you to imagine a coordinate axis set up at the center of the planet Earth and have a line come out of the coordinate axis at the center of the Earth and intersect the surface of Earth right here. This is the equator, which is 0 degrees of latitude, and the prime meridian, which is 0 degrees of longitude. 0 degrees of latitude was picked because the center of the Earth is something we can define geometrically. 0 degrees of longitude was picked very arbitrarily to be the city where this standard was developed. But the reason that these are measured in degrees is because they are literally defined by the angles. The angle formed from the center of Earth, left and right, to the point in question, and up and down to the point in question. Those two angles define the latitude and longitude. And then rho, the distance from the center of the Earth to the point in question, is the radius of the planet Earth. Well, it varies a little bit because Earth is not a perfect sphere, but the definition of latitude and longitude actually does assume that Earth is a perfect sphere. It works, it's good enough, we can deal with it. All right, but latitude and longitude is spherical coordinates, but it's tear your hair out spherical coordinates because real spherical coordinates would set the geometric North Pole as 0 degrees and set the equator as 90 degrees. But that's not what we do because people who do geometry aren't mathematicians and they didn't consult us when they came up with these definitions. I'm sorry. All right, but we have our spherical coordinates and we want to be able to work with these spherical coordinates. So let's see if we can figure out something we can do. In order to do anything with coordinates, we have to come up with some conversions between them. It turns out that converting between spherical coordinates and polar coordinates is quite a bit easier. So that's where I'm going to start. We of course know from our discussion of cylindrical coordinates that this direction in the xy plane is our r direction, and we've seen that we can graph the z-axis and the r-axis and just look at that plane of existence. Our point in question is coming out here, some distance rho, and we know that we have an angle right here called phi. All right, we have an angle, we have some coordinate axes. We probably can find some way of, oh, hey, there we go. There's a right triangle. And so we've got our opposite side here. Z is adjacent the angle. So that's going to be rho times the cosine of phi. And then R is opposite the angle. So that means that R is going to be rho times the sine of phi. And then the angle theta stays the same. And there's our conversion between polar coordinates, spherical polar and cylindrical polar. Now that we have that, we should be able to get to rectangular coordinates without too much further trouble. Right? Of course, I know that x is r times the cosine of theta. And since r is rho times the sine of phi, that means that x is rho times the sine of phi times the cosine of theta. And y is rho times the sine of phi times the sine of theta. Z is the same in cylindrical coordinates and rectangular coordinates. So z is just going to be equal to rho times the cosine of phi. Looking in the other direction, We can get to rho by squaring a bunch of stuff. It turns out rho squared is x squared plus y squared plus z squared. Or because x squared plus y squared is r squared, we have that rho squared is r squared plus z squared. I'm going to come back and have you look at why that is the case a little bit later on. But for right now, we'll accept that, and we can use that in order to rewrite things from cylindrical coordinates into rectangular coordinates or vice versa. To make sure that everything makes sense, we'll start off looking at the constant surfaces. When rho is equal to some constant, well, rho squared is x squared plus y squared plus z squared. So that's the same thing as saying x squared plus y squared plus z squared is equal to that constant squared. We have here an ellipsoid, specifically the ellipsoid where the extents in x, y, and z are all the same. And if you take an ellipsoid and you make sure that every direction is exactly the same length, you realize that we actually have a sphere of radius c. And so our sphere is our constant surface. Whenever we have a surface that we can describe as a sphere, spherical coordinates are going to be the tool of choice. Hey, it's a useful name. That's always convenient. Right? When theta is equal to a constant c, we're going to get the half plane that starts at the z-axis and continues outward. It's going to be exactly the same thing that we got when we were dealing with the constant surfaces in cylindrical coordinates. Phi being some constant is where things get a little bit trickier. Well, instead of thinking about this in spherical coordinates, as I have been discussing for some time, we can take this idea of a constant value of phi and set it into cylindrical coordinates, where I think it's a little bit easier to understand what's happening. So we set our angle phi, and it's a fixed value. And then the value of rho, come on, there we go. The value of rho will let us go anywhere we'd like along this line. And then the value of theta will allow us to rotate this. So if we take a straight line that goes through the origin and we rotate it, we're going to end up with a right circular cone. Specifically in analytic geometry, we call this the half cone, because the full cone that we talked about when we were talking about quadric surfaces is going to involve the positive and the negative direction. If phi is somewhere between 0 and 0 and pi over 2, 0 and 90 degrees, you're going to end up with this half cone in the positive z-axis. If you end up with something between pi over 2 and pi, that's going to be between 90 and 180 degrees, you end up with the half cone below the xy plane on the negative z-axis. And the elliptic cone that we've talked about before had the positive and negative branches going on. So that's why we call this thing the half cone. The naming's a little bit weird because in your study of geometry in middle school and high school, I am sure that you have seen the cone before, and you just called this shape a cone and you've ignored the fact that it was only half of a cone. Um, so a little bit weird, a little bit strange, but it works out. Now, we've dealt with cones in the past. The elliptic cone, remember, was an equation x squared over a squared plus y squared over b squared equals z squared over c squared. In order to make this, instead of an elliptic cone, a circular cone, it turns out that A and B have to be the same thing. So we can actually just rewrite this x squared plus y squared equals some k times z squared. And that value of k will pick how steep the cone is, but it's going to give us the cone with the circular cross section. If we want to rewrite this in spherical coordinates, I've got x squared plus y squared. It would really make my day if I had x squared plus y squared plus z squared, but that's not what I had. Of course, I can just add z squared to both sides of the equation, and everything works out perfectly fine. X squared plus y squared plus z squared is rho squared. Z itself is rho times the cosine of phi. That whole thing is squared. And hey, there we go. It's starting to look like something. Those rho squareds cancel each other out. The square root of 1 over k plus 1 is the cosine of phi. So if we know the value of k, we can figure out the value of phi. If I chose something very simple like k equals 1, then phi is going to be equal to pi over 4, right? Cosine of pi over 4 is square root of 2 over 2, which is the same thing as the square root of 1/2. Choosing other values of k will give you other angles. It's a little bit tricky to find anything that's going to work out nicely. If k is 3, then we will get square root of 1/4 is 1/2, and cosine of pi over 6 is 1/2. So you can figure out the angle that way, and you can go through and get the rest of these. But it does go to show that we can do the conversion. We can go from rectangular coordinates into spherical coordinates, and we do in fact get that that cone is a constant value of phi. One thing that I didn't do in this derivation is when I took the square root, I should have gotten positive or negative, which means that if k is equal to 1, well, cosine of pi over 4 is 1 over, is square root of 1/2, but I could also have negative square root of 1/2, which would mean I need 3 pi over 4. So that's where, again, the half cone comes in, because the top half of the cone would be phi equals 1/4, the bottom half of the cone would be phi equals 3/4. All right. I already told you that I wanted you to do this, but We know that x is rho times the sine of phi times the cosine of theta, y is rho times the sine of phi times the sine of theta, and z is rho times the cosine of phi. We looked at the geometry to see that that had to be the case. I want you to look at x squared plus y squared plus z squared, plug these things in, and work through the properties of trigonometry to prove that this simplifies and turns into rho squared. It's a different way to think about spherical coordinates. It's a chance to review some properties of trigonometry, see what you can do with it, and I'll see you in the next video.